Hello everyone, we are talking about digital modulation techniques and this is a binary modulation technique. Here we are talking about the simple circuit which is going to produce uh, binary digital data in terms of carrier signal based on its amplitude, frequency and phase. So as it is amplitude shift keying, frequency shift keying and the phase shift keying. And for that we are using a simple CMOS switch. As we are seeing it, it is 4051 is a CMOS switch which has been used over here as MUX. I can use it as DMUX, but it creates a channel to select your carrier by with the help of select line, and then it produces your output as it is required, either amplitude shift keying or frequency shift keying or phase shift keying. So one single IC which is very simple, low profile, low cost, low power, but it is going to be used for lots of applications. So let's see, this is amplitude shift keying. The two magnitudes we have decided they are supposed to be produced over the transmission line based on our logic data. This logic data could be, it could be unipolar, it could be bipolar. Normally we say for ASK unipolar is sufficient, but here the option is open for us. So when the pin number 13 is a directly the magnitude is there, and pin number 14 is the low magnitude signal is there. So when the logic 0 comes in, the low magnitude is being selected and high magnitude is being selected on logic 1. So the waveforms they are showing it. Here in this output waveform, we are showing it as logic 0 is a 0 magnitude, but this we can vary it because we are using the potentiometer. So next, if we'll just see to it, it's a frequency shift keying. What we are trying to do is corresponding to logic 1, the one particular carrier should be there, and for logic 0, there should be another carrier. If these frequencies are being selected on the two carrier as carrier 1 and carrier 2 onto the two inputs of our CMOS switch, my select line where the logic data is being given to the pin number 11, that will select, and you are seeing the two carriers. If the carrier is being varied, then the output will remain same, only internal carrier will vary. This frequency shift keying will change based on the digital data. Next, similarly, what we have tried to give it for phase shifting. When the logic data changes, then the phase of the carrier should be changed. No magnitude, no frequency should be varied. And exactly that we have followed. In one channel, we have given the one carrier, and on the other channel, we have given the 180-degree phase shifted. Unity gain op-amp we have used in inverting mode. It's a very simple, and then my logic data has been given to pin number 11, and which is giving me the phase change. Whenever there is a logic change is there you will find the output, there is a phase change. Whenever there is a logic change is there is a change in the phase. So this is the simplest of the circuit which we can find and generate the three different binary phase shifting. And this mux can be used for QPSK, can be used for M-array PSK, can be used for M-array ASK, can be used for M-array FSK, all sorts of application. So this is just uh, a general discussion to help everyone, whoever is interested can develop multiple applications. Thank you.
Same switch has been used but with the two different phases to two different inputs, and these inputs are being selected based on logic data, logic 1 or 0. Logic 1 is showing me the phase starting angle somewhere around, this is going to be on the negative side, and and logic 1 is this angle and logic 0 is this angle. So if suppose switch position 13 and 14, if we are changing it, this phase will be changed. Hold, stop करो, pause करो. Only one single sinusoidal function has been given, that is of 4 kilohertz. If suppose थोड़ा दूर से if suppose this frequency is increasing, it's a carrier frequency is increasing, but logic data change of phase will remain at the same position where my logic data is changing. It does not require any change in terms of frequency. So it's a corresponding to phase, corresponding to logic data, whether its a frequency is less or more. So the carrier is constant in terms of magnitude and frequency, only phase changes are there. So it's a phase shift gain. Logic data again we have taken of 500 hertz. If suppose I want to reduce it, I can increase it. So wherever I am increasing it, after time reduction, frequency increase. So this position is only shifting where the logic 0 starts, where the logic 1 starts. So as the phase shifting is there. If further the time I increased, so the frequency of logic data I have increased. So less frequency, and so depending upon their ages, they are going to show the phases. This is 500 hertz. We have kept the frequency of logic data, whereas of carrier signal we are having the frequency of 3 kilohertz. Magnitude still remains as 1.2 volts peak to peak. Okay. With the phase change corresponding to logic 1 and logic 0. So it's a significantly over there when there is a logic 1 comes in, there is a one particular phase is available, and it is just opposite while the logic 0 comes in over here. So whenever there is a logic changes are there, there would be corresponding phase changes are there, and this we would like to see its spectrum. How does it look like? We had selected the carrier of 3 kilohertz. Yes, it is maximum. Fine, this is 3, and our modulating signal is 500 hertz away, so it is at 3.5 upper sideband, lower sideband, and at the same time the gap of this 1 kilohertz for upper and lower sideband is being maintained at 4.5, 5.5, 6.5, but this center frequency is not very much visible. This is, if I'll just see to it, is 3. It should be visible at, just see 6 pe, है ना? And then here somewhere around here it should be there. 9.
Nine.
So it's a very small. Then ये है ना, somewhere here at 9, and then it is 12 पे. So those harmonics are also there. But here, significantly, there is a drop in the magnitude of carrier signal. But it is sufficient enough to recollect our information. Even if the carrier is suppressed, its advantages, that's all.